100. Okay, we can start, right? Good. And so I already shared the slide. And here you have, we already finished with modulus, right? This is three properties of modulus that we already had last week. And now we are going to another form of complex numbers. You see that actually we can compute addition and multiplication with complex numbers exactly in the same way as what we did for the real numbers. And we have to pay attention to the fact that I square equal minus 1. So this is what we have to take into account when we were working with complex number. But now let's imagine that we want to raise to the power n. If you take x plus iy and raise to the power n, then it's too complicated. You have to use some kind of Newton formula. Right? It seems complicated. So therefore, we need a new form of these complex numbers, and we call this new form is polar or trigonometric forms. So I write here, we consider this complex number z equal a plus ib, which is not 0. Then we write as follow. Okay, of course we have z equal a plus ib, and because g is not 0, so the modulus of z is of course not 0, and therefore we can take modulus of this is square root of a square plus b square as common factor, and then we divide. So we write this way. So draw this modulus out, and the inside will be a over modulus of z and plus ib over modulus of z. So remember, the square root of a square plus b square is exactly the modulus of b of z as defined previously. So actually, you can write this way: it's just modulus of z multiply a over modulus of z plus ib over modulus of z. But now let's pay attention to these two numbers: a over square root of a square plus b square, and the second number is b over square root of a square plus b square. So let's take the sum of the two square. Okay, so immediately you obtain, if you take square of this number plus square of that number, what you obtain, this is actually a square plus b square over a square plus b square. This is 1. You can immediately see that. Okay, the sum of two real numbers, the sum of square of two real numbers 1. This means that we can choose an angle phi. Such that cos phi equal one number and sine of phi equal the other number, right? Clearly, because cos square plus sine square equal 1. So whenever one number can be chosen as cos and the other can be chosen as phi. And if we consider only on the half open interval from 0 to 2 pi, then the angle is unique, right? So we obtain there exists a unique phi in this half interval, half open interval from 0 to pi, such as cos phi equal a over square root of a square plus b square, and psi phi equal b over square root of a square plus b square. And now plug this to the formula of z here. So z, you obtain z equal modulus of z multiply cos of phi plus I psi of phi. So let's write down here. And modulus of z is, by definition, is square root of a square plus b square. And phi is determined by this system star. We denote this system by the notation star here, right? And phi, this phi is called argument of the C. Okay, we can write arg of C, so argument of C. Good, and I will give some name, and the name is this form here. This blue formula is called polar form or trigonometric form of Z. So we call it trigonometric form because it contains cos and sine, you know? But why we call it polar form? So I like the word polar form because it's shorter. If you say trigonometric is okay, but it's a little bit long, you know? So let me explain why we call this form of Z the polar form. Okay, to do this, I return um, to the whiteboard, you know. So let me share the whiteboard. Good. Here you have the whiteboard. Okay, let me draw a picture. So you can see here you have sorry. So I should write in a nice way, right? So you have x or y, and we know this is complex number, and you have.
We haven't seen a whiteboard, sir.
You haven't seen whiteboard?
Oh, okay, it appears now.
I do it again. Can you see this now? Sometimes the network is okay. Can you see it now? Right?
Yes.
So you have here OM, which is Z. Remember, we have two representations in a complex number, complex plane. So you can represent a complex number as a point or as vector. You know? So here we represent as vector, and then with here you have A, and here you have B, right? Good. Then you have this is 5. The angle is 5. So you have this angle here is pi half, you know. This is pi half. So you have this. Actually, you see immediately this angle cos of phi is simply this length is actually A divided by the length of C. You know? So A divided by the length of OM, but the length of OM is modulus of Z, right? And here also 5, and therefore the sine of phi is B over. But actually, this is if you denote it by this is modulus of Z by R, so you obtain something A equal R cos phi, B equal R sine phi. This is exactly the name of this coordinate is polar coordinates. Now that you will learn if you haven't learned, then you will learn in calculus 1. This is called polar coordinates, and therefore the name polar form coming from this type of coordinates. Yeah. So every time when you change to this kind of coordinates, this means you have A is R multiplied cos B, R multiplied sine. This is called polar coordinates. So if you haven't learned this, then you will learn it later, you know, in the calculus 1. So this explains to you why we call this polar form, because it related to the polar coordinates, you know. And now I want to explain. Good. Um, so Now I want to give you some example, right? So we have the formula in the slide already, so what you have to do is to, for example, I consider z equal 1 plus I, right? And we want to change to the polar form. Then firstly we have to compute the modulus. This is square root of 1 plus 1 square is 1, so 1 plus 1 is square root of 2, right? So you write square root of 2 and then you divide by square root of 2 plus I multiply 1 over square root of 2. And now what you have to do is to solve a system cos phi, but it's easy system equal this 1 over square root of 2 and psi phi over 1 over square root of 2, and we require this phi is only on this half open interval from 0 to 2 pi. Then there is only one phi satisfies this cos phi equal 1 over square root of 2, psi phi is 1 over square root of 2. What is this? Can you tell me?
Pi over 4.
Yeah, precisely. You can read pi over 4 or you can read pi fourth. Yeah, there's shorter ways to read pi fourth. And therefore we can write this square root of 2, so cos of pi fourth plus I sine pi fourth. And we finish. So let's do another example. So let's here square root of 3 plus I. Again, you have to compute the modulus. Modulus here square root of, so take the square, you obtain 3. And 1 square is 1, so we obtain this is square root of 4, so we obtain 2. So you write 2, so modulus of this 2, right? So we write 2 here and then you divide by 2. So square root of 3 over 2 and then I multiply 1 over square, no square, now this is 1/2. And now what we want to do is to solve the next. Okay, now the system is cos phi equal, okay, I have to take pencil, square root of 3/2, and here psi phi is 1/2. Now tell me what is the angle here. If you consider phi in the set of real numbers, and it has infinitely magnifying. But if you consider only on this half open interval from 0 to 2 pi, then there is only one, which is, can you recognize this phi?
I over 6.
Good. This is pi 6. You can read pi over 6, or shorter, you can read pi 6. Right? And therefore at the end you obtain this is 2 multiplied cos pi over 6 or pi 6 plus I sine pi 6. Okay, this is nice angle. So this angle and this angle is nice, so we can write pi 4 or pi 6. But now let's go to a little bit ugly angle, say 2 plus I. Okay, now you can see this modulus of z is ugly, so this, 4 plus 1 is 5, right? So we obtain square root of 5 multiply 2 over square root of 5 plus I multiply 1 over square root of 5, right? And now our system star here is something, it's not nice, this is ugly, but even when it's ugly, we can have a way to write down 5. Let me clear this, clear that, right? So now cos phi equal 2 over square root of 5, and psi phi is 1 over square root of 5, right? What does it mean? So we obtain tan of phi is psi over cos now, so 1/2, right? Therefore, and both cos and psi are positive, so you can look at the unit circle and you see as a tan. The angle is not so nice. This is 1/2, but we can write something like arc tan. Yeah, arc tan of 1/2. This is enough now. So therefore, in this, okay, you can write this. We can write this because here's the psi of cosine psi phi here is positive. If there is some negative, so you can write a little bit so minus or pi half minus, whatever. You know? Here we are lucky because it's positive all, so we can write phi is arctan. But when you have some negatives, then you have to choose between minus and plus or pi half minus, whatever. You know? But we can always write down the angle phi here, right? And this in this case you have square root of phi cos of arctan 1/2, right? Plus I sine arctan 1/2. Good. Or even if you don't like to write this way, so use the right or use the right square root of phi cos phi plus I sine phi with phi satisfies the star. This is enough now. Actually, sometimes you don't want to write out what phi is. This is enough. You should write out here. It's the phi is so ugly, you know? Because we know this system determines phi uniquely. If we consider phi only on the interval from 0 to 2 pi, then it's unique, you know? Okay, this is another way to write out complex numbers in polar form. Actually, come what may, we can always write a complex number in polar form. Whatever z is, we can always write z as complex as polar form, right? And it's very helpful because next slide you will see it's very important that we have to change the polar form so that we can do some complicated algorithm, you know? So now we return to the slide and to see what we want to do next. Good. This is polar form of Z or trigonometric form. So there's two names, and I like the polar form because it is shorter. Yeah. So now I will tell you how to compare two complex numbers. It means what's the equality of two complex numbers in polar form. This is our tradition, you know, because whenever we have a new object, we have to know how to see the equality, you know. For example, when we learn about the set, we know how to compare two sets, yeah, how to see that they are equal. When we learn about mappings, we have to see how can we compare that, you know. What happens if we have two mappings that are equal, you know? Or when we learned Cartesian product, or when we learned complex number in canonical form, right? And now we are in the situation of polar form. Then we have the following situation. Of course, you see that we can always change complex numbers into the polar form. Yeah. And z1 is r1 equals theta 1 plus I sine theta 1. R1 is of course, modulus, which is the length of OM, and theta 1 is argument. Similarly for Z2, R2 multiplied cos theta 2 plus I sine theta 2. So these are two complex numbers are equal. Z1 equal Z2. Of course, modulus should be the same because it's the length of the vector represented this number. So the modulus is the same. But the argument, if we consider in the whole line R, then it's might be different by 2k pi. Then the sine and the cos are, because we know that the cos is a periodic function with the period 2k. This means cos of theta 2 and cos of theta 2 plus 2k pi are the same. And similar for sine. Sine of theta 2 and sine of theta 2 plus 2k pi are the same. So theta 1 may be taken any of that angle. If we consider argument on the whole line R, and this is the way to compare. So the modulus should be the same because this is the length of OM. This should be the same. But the argument may difference by cons or by integer multiple of 2 pi. So integer multiple of 2 pi means that 2k pi where k is integer. So let's draw in the picture so that you can see in more detail this representation for equality between two complex numbers. Here, look at this. Again, we return to the um, whiteboard. Lock. Okay. So I delete this, and what we have here. So look at this. So you have two complex numbers that are the same. This means they represented by the same vector here. Z1 equal Z2, of course equal OM. And of course modulus should be the same because this is the length of OM. No other choice. But the angle, let's look at this angle. So you have theta 1, then you have theta 2, of course. But theta 2 may, okay, the first vector is always in this OX, and the second vector is OM. But actually, it can rotate one more round to become here. So we obtain theta 1 may be theta 2 plus 2 pi. It's not only one round, it can rotate more. So 2 rounds, but it still stop at this OM. So it means that it can plus 2k pi for all k in Z. It has the same beginning vector and the same end vector here. The only thing is they rotate more, and you will change this. So they are equal. So Z1 equals Z2 if and only if, of course, the modulus should be the same because it's the length of the vector and the vector is unchanged, but the angle is changed by 2k pi, and it will stop at the same vector here, right? K in Z. Good. So this is for you to see why the angle can be different by 2k pi. Of course, k is in Z. Okay, now we are returning to the slide. And I continue with the slide. Good. Where is our slide? Let me find this. Okay, here. So this is the quality of two complex numbers in polar form. So the modulus should be the same, but the arguments may be different by 2k pi. It represents the same vector in a complex plane. No? Now we consider two operation on this form. So multiplication and division in polar form, right? So let's start by multiplication. So we write z1 in polar form, and we know that we always can do that for any z1. No, whatever z1 is, we can always write as polar form. So z1 is r1 cos theta 1 plus r sine theta 1. Similarly for z2, r2 multiply cos theta 2 plus r sine theta 2. So so we have here I should multiply as usual way, as we are in the set of real numbers. The only thing that I have to pay attention is I squares minus 1. You know? Here I should multiply z1 z2 and multiply these two quantities together. So we have r1 multiply r2, and then the cos plus I sine is multiplied together, and I separate two parts, one containing I and the other doesn't contain I. Now here cos theta and cos theta 2, and here I sine theta 1 and I sine theta 2 actually containing I square, but I square is minus 1. So we obtain this minus, and then the other always contain I is I cos theta 1 sine theta 2 here, and put I as common factor. The inside will be cos theta 2 sine theta 2, the other here sine theta 2 sine theta 1 multiply cos theta 2. Okay, this is just direct computation. But now I am using the trigonometric formulas that you learned in 11th class, right? So this cos theta 1 cos theta 2 minus sine theta 1 sine theta 2, just cos of theta 1 plus theta 2, and this cos theta 1 sine theta 2 plus cos theta 2 sine theta 1, just sine of theta 1 plus theta 2. So at the end we obtain this formula, this blue formula. And actually this is again a polar form with the modular this r1 multiply r2, and with the argument is theta 1 plus theta 2. Yeah? And by chance we prove again the fact that the modulus of a product of z1 z2 is r1 multiply r2. So the product of modulus z1, because r1 is modulus of z1 and r2 is modulus of z2. So modulus of product is product modulus. Again, you see this property at the beginning, yeah, property A, and now we comes by chance again the proof of that equality. And good. So we have here again the argument of a product, simply the sum of two arguments here, theta 1 and theta 2 here. Okay, so this is multiplication. So the multiplication actually very simple. You just multiply two moduli, and you just add two arguments. Yeah. For division, now we have to have the fact that the denominator here is different from 0, and we divide. So z1 over z2. When z2 is not 0, then we can divide. And actually this is easy. So it's divide by 2 moduli, and for argument you take the minus, theta 1 minus theta 2 plus I sine theta 1 minus theta 2. Actually, if you want to prove this equality, it's very simple. You just multiply with denominator and you apply the above formula. Yeah? Because you multiply denominator on here, then you multiply modulus that you obtain R1 and you add two argument minus theta 1 minus theta 2 plus theta 2, again you obtain theta 1. So actually you obtain the numerator here. And again, by chance, we prove this again. The modulus of a division is a division of two moduli. Yeah? An argument of a division is difference. Yeah? Two arguments. Yeah? Good. We will apply that result into our problem of power. Yeah? So we start with integer power. So you see this is very easy because pay attention to that formula here. Now if R1 equal R2, then this become square. Now theta 1 equal theta 2, then you obtain 2 theta 1. So this is what I am doing here. So for z equal r cos theta plus I sine theta, when I take the square means that I multiply this double. So r cos theta plus I sine theta multiply with itself, then you obtain r multiply as r square, and theta plus theta is 2 theta, right? Simple. And this can be done for any power which are positive and integer. So I take n natural number n greater than 0, because n equals 0, then z to 0 equal 1, so we don't care about the k n equals 0. So let n greater than 0, natural numbers, and z to the n means that this r cos theta plus I sine theta to the n. We just write down n times, and we just multiply on r here. How many r? So we have r, so n number r, so this is r to the power n. Yeah? And theta here you just add how many cos here, how many theta in cos, so you have again n theta, so you add theta plus theta n times, so you obtain n theta. This is the same way as what we are doing here, but the only thing is you have more terms. So you have more theta and you have more r, and you obtain here exactly you have n number r and n times theta. Exactly you have r to the n and cos n theta plus I sine n theta here. Right? So you are done. So you obtain this formula. True for all n in the set of natural numbers. In k n equals 0, which means that something to the power 0 is 1. But now let's consider n an integer but negative integer. Then what happened here? When n is negative, of course it's still integer. So n in z, but n is negative. So we have the following trick. So we write as r multiply cos theta plus I sine theta to the power n. Good. So we write n as minus 1 multiply minus n. Therefore, we can write as follow. Firstly, we raise to the power minus 1. And then raised to the power minus n, and we just use the fact that minus 1 multiplied minus n is simply n. Yeah? And here, of course, you have r multiplied cos theta plus r sine theta to the power minus 1 is simply 1 over this r multiplied cos theta plus r sine theta. And now we are lucky because minus n is now positive integer, because n is negative, so minus n is positive. Okay, now we want to apply the formula for the division. Yeah? So the division formula is here, but therefore we want to change number 1 to the polar form, right? Yeah, but it's easy. So number 1, can you tell me what is polar form of number 1? Modulus is 1, so 1 multiply what? What is the argument of
Cosine 0.
good? Yeah, this is exactly as what he said. So 1 multiply cos 0 plus I sine 0 divided by this r cos theta plus I sine theta. So we just divide the modulus here, you obtain 1 over r, and you take the difference theta 0 minus theta, you obtain minus theta plus I sine minus theta. Okay, now you have already you have here the polar form, and now minus n is positive and integer. Then you can apply the blue formula here, because this blue formula is true for n in the set of natural numbers, right? So that applies that formula. Then you obtain this is 1 over r to the power minus 1. This is 1 over r to the minus n, and cos of minus n multiply minus theta plus I sine minus n multiply minus theta, and 1 over r to the minus n is just r to the n, and then cos n theta, because n minus n multiply minus theta is simply n theta plus I sine n theta. Okay, at the end of the day, you obtain this formula for all n in Z, right? Whatever, negative or positive, is always true for any integer number. Good. And okay, let's of course in the special case when r equal 1, then the formula has a name. The name is de Moivre. This is again a French mathematician, you know. So when r equal 1, so you don't have to write 1 anymore, because 1 multiply anything is anything, you know. So this is cos theta plus I sine theta to the n equal cos n theta plus I sine n theta. So sometimes you use this Moivre formula to compute cos n theta with respect to cos theta and sine theta. For example, if you put here 2 and you compute the square, and then you equate with the right hand side, you obtain cos 2 theta will be cos square minus sine square. Sometimes like this. And if you want to compute cos 3 theta with respect to cos theta and sine theta, you just use n equal 3 here and compute. So you can use any n here. But now I want to give example for that blue formula here. So again, to show you example, we return to the whiteboard. Again, I return to whiteboard. Hopefully it's again here. Good, it's again here. So we I clear the canvas. Okay, let's raise to the power of 1 plus I to the power 7, for example. Firstly, what we have to do is to change this 1 plus I to the polar form, but we can change this. Whatever complex number is, we can always change to the polar form. But this is what we already did before. So you obtain this square root of 2 cos pi fourth plus I sine pi fourth, right? And raised to the power 7. And here you have you use the formula, the blue formula, and you have this square root of 2 to the power 7. You can write simply 2 to the power 7 half, so that you don't have to too much. You don't have to write too much square root. Yeah? So I write here 2 to the power 7 half, and then here cos pi over 4. So we can read cos 7 pi fourth. You know? I sine 7 pi fourth, and now we compute further by using the fact that this is pi fourth plus pi. Yeah, then you can compute. Yeah, you can do this further. But actually, you can compute generally, not only for n equals 7, but you can compute generally. You have 1 plus I to the power n. What you have here is again you use this square root of 2 cos pi fourth plus I psi pi fourth, and then raised to the power n, right? And what you have again here, you can write as 2 to the power n half. Similar here, is replace number 7 by general n, and here is a have codes of n by fourth plus I psi n by fourth, right? Okay, let's do one more example. So let's do square root 3 plus I to the power whatever, you know, to the power n, for example. Then as above, firstly we have to change this square root of 3 plus I to the polar form, but we already did it before. So the formula is 2 multiplied cos of pi 6 plus I multiplied psi of pi 6, right? Raised to the power n, and here you have 2 to the n by formula that we had before. Multiply cos of n pi over 6 or n pi 6, yeah, plus I sine n pi 6 or n pi over 6. Good. And whatever, yeah, you can do any, even when the angle is not nice, and you just try cos of phi or cos of arctan or something, yeah, no problem. Okay, I return to the slide, and we will do some more important operation. Yeah, so this is raised to the integer power. Actually, it's true for any integer, you know, not only natural number but also integer. And we want to do more complicated operations. This is the root. So let me return to the slide. Good. And here I'm going to the root. Okay. What we want to do is we want to compute nth root of this c. But let's do it in easy way. Yeah? So I give you the following problem, and the solution of this problem actually gives us the n roots of this complex number z. Yeah? So the following. Okay, but now it's time for short break. So we have 10 minutes short break. Yeah? So I will resume after 10 minutes. Okay, see you later. Take a short break for 10 minutes. đúng không? Okay, we continue. Cái gì nhỉ? Good. Where's my slide? Okay, I found this. So this is our problem now. So given a complex number z and a number n, so the natural number positive, so n star means that n minus 0. So this number n is natural and positive, so positive natural number. Let phi owns the w, which is complex number such as w raised to the power n equals z. This means we want to find n root of z. Instead of finding that, we find w such that w to the power n equals z. And we know that if we use the polar form, then we can raise to the power easily. So therefore, our solution going as follows. So we use the polar forms for z and also for w. Of course, z is given, so we can compute r and theta directly. But now we also write w in the polar form. Suppose it has a form rho cos phi multiply cos phi plus I sine phi. And what we have to do is to find this rho and this phi, such that w to the n equals z. Good. Here we have r and theta, of course, given. Actually, we can find, we can determine what r is and what theta is, because these already raising to the power n of this w. Here we obtain rho to the n cos n phi plus I sine n phi. And on the other hand side, we have g, which is r cos theta plus I sine theta. And now we apply the equality of complex numbers in polar form. So the modulus should be the same, but the argument may be different by 2k pi. So we have rho to the n r equal r and n phi equal theta plus 2k pi for all k in z. This is the same as that. So actually now rho and r are positive number, right? Therefore we just take the real positive root. So we have rho equal n root. So this is a real positive n root of r. So I just write r to the power 1 over n now. And then we have phi equal theta plus 2k pi over n, where k running on over this set of integer g. Actually, we are afraid that this seems that this angle phi has infinitely value, because here k running on over the set of integer z. So we are worrying, but actually there are only n distinct values of w. I will explain why. This is corresponding to k equal 0, 1, blah blah, until n minus 1. Let me explain to you why we have only n distinct values of w. Because here you have, if you run one more step, so k equal n, and then we look back as a case when k equals 0, and we take the difference of the angle in these two situations when k equals n and k equals 0. So for k equals n, the angle is theta plus 2n pi over n, and when k equals 0, then the angle is theta over n. So the difference is actually 2 pi, and therefore they represent the same vector, no? Because the difference is 2 pi, and therefore the value of w corresponding to these two situation k equal n and k equal 0 are the same, because the difference is simply 2 pi. Yeah, when the argument is different from integer multiple of 2 pi, then the complex numbers are the same. Of course, here we have already the modular is already the same. No? Similarly, if you run one more step, so k equal n plus 1, and we compare with k equal 1, then these are two values of w again the same. So we can say simply just k plus k equal n plus 1 and k equal 1 is the same value of w, because the difference again 2 pi, and so on. So actually we have only n distinct value, because here you can see that you take any two situation here, you take the difference, and the difference between 0 and 2 pi is smaller than 2 pi, then the values is its own way different. You know? And we are lucky, so we have only n distinct values, so don't worry about infinitely value here anymore, right? Good. So let me write down the w to the n equals z equals this polar form depend only if w is one of the following values. So I write down here. I should rewrite the value here, no? So the modular should be r to the power 1 over n, and the argument here is theta plus 2k by n plus I sine theta plus 2k pi over n, where such that k running on over from 0 blah blah until n minus 1. This is not a single value. This is a set containing n values, and different values, and distinct values. Therefore, we have to write as a set. Yeah? And so let's give this set some name. Yeah? And some notation here, and the name and the notation are here. I write here. So for z equals is r cos theta plus I sine theta, we denote n roots of z to be this set. You know, the set of all values such that when you raise to the power n, you obtain z. You know, so the set will be of the form r to the minus 1 over n multiplied with cos theta plus 2k pi over n plus I sine theta plus 2k pi over n, such that k running from 0 to n minus 1. And this set is called the set of all nth roots of z. So every member of this set, when you raise to the power n, you obtain z. Therefore, the set is denoted by nth root of z. Yeah. And therefore, after review the computation, we see that w to the n equals z if and only if w belongs to this set. No, this is I rewrite here. So w to the n equals that r cos theta plus I sine theta if and only if w is one of these values. This means w belongs to this set. No, so this is you cannot write equal here, because you have on the hand side here you have a set, and on the other hand side you have a value. Therefore, we have to write W belongs to. This is exact way to write W to the n equal the value r cos theta plus I sine theta here. It's equivalent to W belong to this set. You know? And the set denoted by an nth root of z. You see, this is not a single value. This is a set of n values. So we write as a set. You know? Okay, let me give you a very important notation. So notice that so when n is positive natural numbers, we have just this nth roots of z always contain n different value. We already saw this last line, huh? And exactly when you say about complex number, complex roots, then nth root of z always contain n different value. Let's see immediately by an example, you know? And of course, for w belong to this set nth root of z, then we call w an nth root of z. You know? N, because here you have a value, and when you have here nth root of z is a set, so value belong to the set. That's very standard way to write n roots of z. You know? So let's give you an example here. So let me raise a little bit bigger so that you can see it better, right? Good. So you see, now we are considered complex root, third root, of 1. Of course, if you consider real root, then it has only one value, which is 1. If you take third root of 1 and consider it as the real root, then it's only one value. But if you consider the complex root, then remember that whenever you take the nth root of a complex number as complex root, then this set always contains n different value. So you have to write all it down here in this way. Of course, then you have to change this number 1 into the polar form, but we already did this before. So don't worry, we already did this here. And we write this 1 multiplied cos 0 plus I sine 0 clearly. And here you have 1 multiplied. So by definition of this set, nth root of c, so it's contained of n to the power 1. And so this is n to the power 1/3 is still n. Yes? So with the right 1 here, or you don't have to write anything because 1 multiply everything is again everything. Yeah? So 1 multiplied is equals to 2k pi over 3. In this case, n equals 3. N here equals 3. And 2k pi plus 0. So the angle theta is 0. So you obtain 2k pi over 3 plus I sine 2k pi over 3, and k running from 0, 1, 2. So there are exactly 3 values because we know from theory that the nth root of z always contain n distinct values. So let's write down because there are here only 3 values. So I will write down. So for k equals 0, you obtain cos 0 plus I sine 0. It's actually only 1. And then k equals 1, you obtain cos 2 pi over 3 plus sine of 2 pi third. Actually, it's minus 1/2 plus square root of 2/2 I. And the last one, when k equals 2, then you obtain cos 4 pi third plus sine 4 pi third minus 1/2 minus square root 3/2 I. Good, this is simple way. But even in this simple way, I want to emphasize that if you compute the complex roots, then it's only contain exact and different values for nth root of z. Good, and now we go to another example here. So let's compute this Okay, let's good. So z equal 1 plus I. So firstly you have to change it to the polar form, but it can be done easily. You know, actually we already did this before, and is it right now square root 2 goes pi over 4. Of course you can reach pi fourth plus I sine pi fourth and whatever. So you have now let's compute the fifth root of 1 plus I. Actually this set will contain 5 different elements, and so you take square root of 2 to the power 1 over 5, so we obtain 1/2 multiply 1 over 5 is 1 over 10, so we obtain 2 to the power 1 over 10 goes the whatever. No? So this is pi 4 plus 2k pi over 5 plus I sine pi 4 plus 2k pi over 5, where such that k running from 0 to 4. So we have to let k running until you obtain exact 5 element here. Yeah. So from 0 to n minus 1, n equal 5, so we obtain from 0 to 4. You know? So we do some computation, so it look nice. So you can put here, okay, this is not so nice. You can put pi outside and you obtain 1 plus 8k. You know? Good. And this is the set of all fifth root of this 1 plus I. You know? And of course, maybe I give you one more example so that this is familiar to you. You know? Let me return to the blackboard, to the whiteboard. Where so no, I need whiteboard. Good. So let's share. Here's the whiteboard. Okay. So we clear the canvas, and here you have what I have. Let's compute the nice root of so big now. So I write in a nicer way. So it's 9 roots of square root of 3 plus I, right? So the first step you have to change the number under the root here to the polar form. So as above, we already did this, you know. This is called pi over 6 plus I psi pi over 6, right? And good, so we obtain this is 2 over power 1 over 9, and then cos pi over 6 plus 2k pi, and then over 9 plus, okay, if you are careful, then you make one more bracket here, and then I psi of this pi over 6 plus 2k pi over 9, such that k running from 0, 1, 2, blah blah until 8. Yeah, good. And you can write in a nicer way. You do some computation, yeah, and at the end you obtain this is cos of what is this 8 6 multiplied 2 is 12 k plus 1. You can put pi outside, and you divide by 9 multiplied 6 is 54, right? plus I sine of this 12k plus 1 pi over 54 brackets such that k running on over from 0 blah blah until 8. You know? Good. This is on the set of all nice root of this number, right? Good. And you can do any root, you know, for any complex number. And remember, the n root of z when n is integer, the set of natural number, and n greater than 0, so n of course greater than 0. So positive natural number always contain exactly n different, you know, value, no more no less, you know, exactly n. Good. Now we are going to the next root, which is square root. I want to introduce this because this is helpful when we construct the formula for the quadratic equation. You know? Actually, you have here. Let me return to the slide. Right. So you have here the slide. Where's my slide? Here, of course. Good. Okay. So you have here. I go to the square root. And we see that for square root, good, we have here, we consider this any complex number z. Of course we can change to the polar form r cos multiply cos theta plus I sine theta, and we compute the square roots now. And actually we knew already that the square root only contain two different values, of course, when z is not 0, because if z is 0, then nothing to say, you know. So let's compute this. Okay, so you have here square root of r multiply cos theta plus I sine theta. So by the formula as above, we have the real root, real square root, real positive square root of r. This is a real positive root, and then cos theta plus 2k pi over 2 plus I sine theta plus 2k pi over 2, where there are only two values here, so corresponding to k equal 1 or 0. And what happened? So okay, you see here that good. Actually, when k equals 0, it has a form square root of cos theta half plus I sine theta half, and k equals 1, you obtain cos theta plus 2 pi over 2. So this means cos theta half plus pi plus I sine theta half plus pi. Can you see that that value is just minus of the first value? Yeah. Let me explain to you. So the second value corresponding to k equal 1, just the minus of the first value. It seems coincide with the real root now. Let me explain why there is so nice here, so nice result here. Okay, let's return to the blackboard, to the whiteboard. What we had here is something nice. This means that the square root contains two opposite value, plus or minus. Plus or minus. Okay, so you have, let's draw unit circle. So you have here the angle phi half, theta half, for example, and then you have theta half plus pi. Then actually the sine, of course, opposite to each other, and the cosine opposite to each other, and the sine also opposite, because this is pi, theta half, and this. So they have the same line here, but this is the opposite direction, no? So what does this mean? This means you have cos theta half plus pi plus I sine theta half plus pi is simply minus the cos theta half plus I sine theta half, and therefore you obtain square root. If you put this is by w, then square root of z contain two value w and minus w. Yeah. So therefore we can write, it's not so exact, but it's very convenient. Just write plus or minus w. No? Actually, if you want to write exactly, then you have to write, because it's a set, no? Then you have to write as a set. But because in this set there are only two opposite values, no? W and minus w. So we are allowed to write in easy ways as plus or minus w. Good. And this is now time to return to the slide again, and to obtain some. Okay, here I already write in the whiteboard, but now I rewrite here. So when z is not zero, so we knew previously that the square root of z contain only two values, no? But now in this case, after discovering this here, we obtain that contain two opposite value, w and minus w. So we write simply for convenience, yeah, we just write plus or minus w. When w is one of the square root, then the other square root should be, the other value of square root should be minus w. And it's helpful when we are considering the, okay, there is a practical formula that I want to give you here now. So you want to compute it fast, z equal x plus iy, then immediately we can prove that square root of z contain two opposite values. Now the first value w we can compute by square root of 1/2. This is modulus of z plus x plus psi of y, where the psi function is 1 if y greater than 0 and minus 1 if y less than 0. Multiplies I multiply square root of 1/2 of modulus of z minus x. This is practical formula. You can compute directly square root of z. The proof is easy because you just take the square of that. Then after some easy computation, again you obtain this x plus iy. After you raise to the power 2, yeah? Then you can obtain this. You can try, as homework to prove when you raise to the power 2, so you take the square of that term, you obtain x plus iy. Let's do it at home. It's not so difficult. This is a computation. Okay, let me take an example. So z equal minus 8 plus 6y, 6i, and here immediately you obtain the modulus is square root of 100, so 10, and x equal minus 8, y equal 6, and immediately from this the psi of y is 1 because y greater than 0. Then you put it to the formula, and immediately, that you obtain square root of z, in this case plus or minus 1 plus 3i. So immediately, this formula is not so difficult to remember. And Okay, then now we can return to the quadratic equation with the coefficient in C. No? Actually, if you are consider quadratic equation in the set of real numbers and you consider the real root, the real solution. So the solution of quadratic equation are called the roots. No? Instead of saying solution, we say roots of quadratic equation. So this is the tradition. If you consider in the set of real numbers and consider only real roots, then quadratic equation may not have real roots because when you take the square root of negative numbers, then it's do not have the real root anymore. Huh? But if you consider the complex roots, then it always has solution, has the roots. Yeah? So the formulas of the root is the same as before because the computation is exactly the same. It's nothing changed here. Yeah? So you have z equal minus b plus or minus w, where w is square root of delta. Delta is b square minus ac, right? You see that here um, because square root of delta is of course plus or minus w, right? So I just write here, but this seems difficult to remember, you know. Therefore, practically you can remember this way: minus b z equal minus b plus or minus square root of delta over 2a, you know. And of course, when you have so make it smaller. When you have the fact that a, b, c are real number and delta, of course, this time is also real number, and delta is less than 0. Normally, if you consider the real root, the real solution, then there is no real solution in this case. But if you consider complex solution, complex roots, then it again has solution. And this, in this case, square root of delta is simply I multiply real square root of absolute value of delta. So this is plus or minus here. You know? In this case, only in this case we can have this formula. You know? Okay, let's see. Let's see this an example here. Z square minus 5 plus I z plus 8 plus I equals 0. Well, and let me show this using the practical formula for square root. So look at this. So let me return to the blackboard, and of course I write here the equation first. So you have equation is z square minus, so you have z square minus 5 plus I z plus s plus I equals 0. And now I share the blackboard as a whiteboard 8 plus I. So that you can see how easy it is to show quadratic equation on a complex, on the set of complex number, on the field of complex number. Here our equation is thus. Now let's compute the delta, and then so we have delta equal 5 plus I square minus 4 multiply h plus I. So this is b square minus 4ac, it's delta. And after computation, what do you obtain? Can you compute fast? Actually, it's minus h, plus 6y, 6I. Yeah, and this is sample to compute. So you can apply the formula that I gave you, a practical formula that I gave you before. What is practical formula? Square root of z for z equal x plus iy is a plus or minus, because we know that the square root always contain opposite value. No? So, square root of 1/2 modulus of z plus x, yeah, plus psi of y multiply I, and then multiply square root of 1/2 modulus of z minus x, something like this, yeah. And actually we already computed in this line, no? Okay, we already computed here. Then you obtain plus or minus 1 plus 3i, no? Is plus or minus here, so you obtain square root of minus is plus I6 or 6i if you like, is plus or minus. This own way has two opposite values, so I can write plus or minus. This is square root of a complex number, 1 plus 3i's. So and then this quadratic equation equivalent to the following solution or roots: z equal 5 plus I plus or minus 1 plus 3i over 2. So it's become, so you have one of the two roots. The two root is it take plus, and this is 4. What is this? 1 not 4. 1 plus 1 plus 5 is 6, so you obtain 3. And 2i. And if 1 minus, you obtain 4, so you obtain 2. And I minus 3i is minus 2, so you obtain minus 3 minus I. So this is easy, but sometimes maybe I give you more difficult. Sometimes the problem is another example is you can consider this x to the 6, right? Minus 5 plus I, z to the 3, for example. And here we have to change the variable. So by putting t equal z cube, no? Z cube, then equation become t square plus minus 5 plus I t here plus 8 plus I equal 0. And here as above, see above, you see that you can solve t equal, actually the equation here t square minus 5 plus I t plus 8 plus I is exactly the same as this equation here. It is the same here. Then by the above solution, by the above rules, we already obtained this t equal 3 plus 2i, or t equal 2 minus I, and this is equivalent to z cube equal 3 plus 2i or z cube equal, and now you can take roots, yeah, third root. We already knew how to do this, so let's do it as homework here. Yeah, it's easy now because now you can take the third root, yeah, and let's do as homework. And there is some other exercises in the same spirit. Yeah. You have to change the quadratic equation and then you show and then you change to the original equation by substituting t by the original variable. No? Good. This is complex number. And now we are going to the next slide, which is our main subject here, matrices. You know? So there are some example of matrices that I gave at the beginning as motivation for the subject. You know, you already studied this, already see a matrix, and of course now I go to the detail of matrices. You know? Good. So let's see. Let's start by a basic concept. Again, we consider field K, which is R, the set of real numbers, or set complex numbers. No, but most of the time we are working with real numbers. So let's think about K as a set of real numbers, so that the problem is easier for you. No. Then we can define a matrix simply a rectangular array of numbers of this field K, R or C, enclosed in a bracket, yeah, and these numbers are called entry or element of the matrix. So you can see here, so you have here a rectangular array, so here you have 2 rows and 3 columns. Actually this is a rectangular array, you know, and each entry here are numbers, real numbers, you know, and we use a brackets here. But there are two types of brackets that you can use. If you don't like this square brackets, then you can use the round brackets if you like. You are allowed to use one of the two types. You know? Square brackets as what I use here, or round brackets. Yeah, sometimes we can use round brackets. Good. So you have here another matrix, only 1 column, 2 rows. Here it's only 1 row and 3 columns. Here 2 rows, 2 columns. So that a rectangular array of numbers, you know? And the numbers here in the matrix are called entries of matrix. And some more notation. And of course, the example that I gave you here is not so interesting as what I gave you as the motivation at the beginning of the subject. No, but let review it here. Here, let's see some example from our real life. So change future, for example. So suppose we are in a shop, and there are 3 products, 1, 2, 3. And here is the table that record the numbers of chains of each product. For example, here on Monday they showed 10 product 1, 0 product 2, and 0 product 3, and they are recorded in the column, right? And the next day, Tuesday, the numbers of chains of each product are recorded in the second column. Blah blah. At the end of a week, you obtain a table. You obtain a rectangle array, and actually this is the matrix. Good. And then the most important examples that I gave you here, the system of equation, as in the motivation that I gave you at the beginning. So here you have a linear equation, and now if I record every coefficient here arranged in the rows, and then I had the matrix of coefficient. So say here the first row is coefficient here. I consider only the left hand side here. So you have here coefficient here arranged in the rows. Second equation is on second rows, and I recall only the coefficient. Then you obtain a coefficient matrix that we will learn later. Also, this is what we will need later. And this is a matrix. It contains 3 rows and 3 columns. And each entry here are real numbers. Now, so number of a field k equal r. In this case, the field k is simply the set of real numbers r. And some more notation here. Traditionally, we use the capital letters ABC to denote matrix, but sometimes you can use a lowercase letter also. With the zero entry, so is JK in the bracket here. We two indexes now because an entry belongs to row and here indicates the rows that it belongs to, and the second index here indicates the columns that the entry belongs to. So the A sub JK means that this is the entry in the raised row and case column. So look at this A. So A11 will be 5. So the entry in the first column is 5. You write down that A sub 11 will be 5. Okay, look at this here. And A sub 12 means that the entry on the first row and the second column is minus 10. A sub 2, 3 means that the entry on the second row and third column should be minus 2 and so on. Good. And we have this following definition about the size of matrix. By an m by n matrix, we mean a matrix n rows, and each row are called row vector, and n columns, and each columns are called column vector. So here I want to emphasize on the way how to read this symbol. This is not a product, but this is a symbol to indicate the size of matrix how many rows and how many columns it has. So here you should read as m by n, not n times, but m by n. This is a symbol that indicates the number of rows and number of columns that a matrix has. Good. This is, for example, so generally, if you write general way, and m by n matrix A actually has a form. So you write all the entries, and the first row, of course, has the first index only 1 because this is indicates the row that the element, the entry belong to. So the first, every entry in the first row have the first index that is 1 because 1 is the first. So the first row, so the first index is 1, and the second row, the second row should have the first index 2 because in the second row, blah blah, the m row should be first index is m, right? And if you look at the column, then for example, the second column should have the second index here. Every term, every entry here should have the second index 2 because it belongs to the second column, right? Good. And special case, when m equal n, this is the number of rows, the same as number of columns, then the rectangle becomes a square. So we call this n square matrix. or n by n, but n by n is the two numbers the same, so we call this n square matrix. And in this case, when m equal n, so there is a diagonal going from a11, a1, a22, blah blah until a nn, you know, because here m equal n. So this diagonal containing all the entry a11, a22, blah blah until a nn is called the main diagonal or principal diagonal of A. No? So this here, when m equal n, this is a diagonal running from this corner above left corner until the below right corner. No? Then this is called main diagonal or principal diagonal. And I give you also the notion of vector. So a vector is simply a matrix that has only one row or only one column. No? So if it has only one row, then we call it row vector. If it has only one column, then we call it column vector. And here is an example. And of course, the name, when you have a vector, then entries of vector are called the components. No? Components. Here, you have here example of row vector, because the matrix has only one row, and it is called row vector. No? And here, the entry here are called component. You see the first component, second component, blah blah, the last component. No? Whereas this B is only one column, so we call this column vectors. And here the entries here are called components. First component, second component, blah blah. The last component. Okay, and now we are going to the next actions. So operations, the transposition of A now. So given a matrix A, then the transposition AT of an m by n matrix A is the n by m. So there is an interchange between the number of rows and number of columns here. So where A is n by n matrix, then AT is n by m matrix that has the first row of A as its first column, second row of A as its second column, blah blah, and m rows of A as its mth column. This means we write row of A as column, then you obtain AT. Yeah? Correspondingly, the first row of A is written as the first column of AT, the second row of A is written as second row, a second column of AT. So let's draw a picture. Here you have A. I color the row so that you can recognize easy. You know? So the first row is blue, the second row is green, the last row is red. And here it has m row and n column. And you have AT is constructed as follows. Firstly, the number of row of AT is n. It's the same as number of columns of A. And the number of row of AT is m. The number of columns of AT is m, the same as number of row of A. This is because we write row of A as column. Yeah? So the first column of AT simply is this first row. Yeah? And the second column here, of course, you can see this green row. Yeah, right? And blah blah. And until the last column of AT is the last row of A. So we write, actually, the principle is very simple. You should write row of A as column of AT. Yeah? This, so therefore, the number of row of AT actually n row, and the number of column is m, because we write m row here as column. So the number of columns of AT is exactly m, and the number of row of AT is n. No? It's interchange the numbers of row and columns. And you can see here example so that it's easier when you see a concrete example here. So you have 1, 2, 3, 4, 0, 7. So you just write 1, 2, 3 as columns, 4, 0, 7 as another column. So, okay, by definition, each column of 80 is correspondingly row of A. Now, so you just write row of A as column. Good. But there is another way. So if you don't like that way, then there is another way. The other way as follow. You write column of A as a row of 80. So this is A11, A21, AM1. Exactly you see here. A11, A21 is a row of 80. Yeah. And you obtain the same. So the second column of A, A12, A22, AM2. Exactly the second rows of 80. Okay, look at this example. So if you don't like the previous way, that is to write row as column, you can use the following way. So you write column as row. So 1, 4 here, write as row 1, 4, 2, 0 here, 2, 0, 3, 7 here, 3, 7 here. So there are two ways to construct this 80, and you obtain the same matrix, which is called transposition 80 of A. You know? Good. So now we have the first important addition here, the matrix addition and scalar multiplication. But we want to compare two matrices. Yeah. As above, when we have a new object, first thing that we should do is we should know how to compare this new object. Yeah? How to see the quality of two matrices. So the matrix is a little bit more complicated because it has the size, this means the number of rows and number of columns, and then it has the entries. So therefore, firstly we define two matrices are said to have the same size if they are both m by n. They have the same number of rows m and the same number of columns n. And when does it happen? This means when they are both m by n, then we say they have the same sizes. And of course, when two matrices already have the same sizes, then we can compare. Then of course, if they are of different sizes, then of course they are different, of course. So two matrices A equal AJK, B equal BJK. We say that A equal B, you know, if and only if they have the same size, of course, then we can compare, you know. So the same number of rows, the same number of columns. This is called the size of matrices, you know. And also the corresponding entries are the same. So the entry on the raised row and case column of A the same as entry on the raised row and case column of B. So AJK equal BJK. True for all J and for all K. You know? Actually, two matrices are the same, are equal if they look exactly the same. It's very simple, but I should write here as a first thing before we can do further operation. And now we can define the addition and multiplication. You know? So scalar multiplication. So we define matrix addition as follow. Again, we consider AB. There are two matrices of the same sizes now, because they are both m by n. Then the sum, of course, written as A plus B, defines very simple. It's just obtained by adding the corresponding entry. Here I write here so that you can see easily. So A plus B means that you have an m by n matrix with the entry AJK. And here another matrix B is also has the same size, so m by n again with the entry bjk. And then to add these two matrices, use it as the corresponding entry, yeah, ajk plus bjk. And here look at this. Of course, before I give you an example, use it. Pay attention that matrices of different size cannot be added because there are redundant now. If there are some redundants and we cannot add, so this means that matrices of different sizes cannot be added. And here example, so A is the size 2 by 3, and then B, if you want to add A with B, then B and A should have the same size, and B should be 2 by 3, no? And then use it add corresponding entry. So here the entry in the first row and first columns, here first row and first column, so use it add 2 plus 2. And here second row, second column, add with here second first row, second column should be added with first row and second column. Yes. Correspondingly, this is easy. You know? This is just for fun, but this is important later you will see. You know? So use that add corresponding component. So -1 here should be added with 5 here. Yeah, this is first row and third column here. So it should be added with first row and third column here. Similarly, 1 plus 7, 4 plus 1, 2 plus 4. Correspondingly, this is really clear. And of course, it's easy. But now we are going to even easier operation, which is scalar multiplication. Scalar multiplication means that we want to multiply a matrix, so m by n matrix A, jk, multiply it to a number c. So normally we call number scalar. You so number in a few k normally is called scalar. So the multiplication here is called scalar multiplication. Then this product of a matrix and a numbers is defined as follows. Ca, this is notation, is that multiply C with all the entries of A. So this means the product C multiply A is obtained by multiplying X entry in A by C. So you use it multiply C to every entries of A here. So before I give you an example, I give some remarks so that you can see immediately. It's really easy to do this scalar multiplication. For example, here you multiply -1 with A. This means you multiply -1 with every entry of A, and every entry of A become opposites. So therefore, we denote this scalar multiplication by -A and call negative of A. Yeah? Number 2, minus k multiply A the same as before. We can write as minus ka, and if you have A plus minus B, you can write as A minus B. Yeah? So later on you will see the reason why. And A minus B, that means that I add A plus minus B, and minus B, that means that -1 multiply B. You know? So, and we call that the difference of A and B. So the difference, that means that the addition of the opposite element. Good. So I have here example. So here's A. Two, 5, -1, 4, 3, -7. When I multiply 2 with A, means that I multiply 2 to every point, every entry is here. So 2 multiply 2 is 4. 2 multiply 5, 10. 2 multiply -1 is -2. 2 multiply 4 is 8. 2 multiply 3 is 6. 2 multiply minus 7. Oh, here should be minus. No, there's some mistake here. I have to change. Okay, wait a moment. So I have to change to minus here. So wait me some seconds so that I can change this. Um, okay, good. So I finish this and we can see a new one which is exactly, you know. So we have 2 multiply minus 7 and it should be minus 14. You know, when you multiply 2 with minus 7 it should be minus 14. Okay, so minus a here should be, this means you multiply minus 1 to every element of a, and this means you change all the sign of the numbers here, to the opposite sign, right? So this is minus 2, it's minus 5, 1, minus 4, 3, 7. Good. And this very special case, when you multiply 0 with a, what do you obtain? You see immediately that you multiply 0 with every entry of a, and whenever you multiply with 0 you obtain 0 number. It's clear, no? And therefore this is very special matrix, you know? All of the entries are 0 and it deserves a name, and I will give it a name, and the name is 0 matrix. Now, this is a definition of 0 matrix. So you have an m by n 0 matrix is an m by n matrix with all entries are being 0, and we denote just m by n 0 matrix by this 0 m by n, or by 0 if mn are clearly understood, right? Sometimes in some concrete situation we already understand what mn are, then you should write simply 0 to indicate this is 0 matrix. So what you have here, let me give you an example. Here you have 2 by 3 0 matrix. This means this is a 0 matrix that has a shy 2 rows and 3 columns. It's 2 rows and 3 columns. All the entry are 0. Yeah. And here you have 0 multiply a is 0 matrix for all matrix A. So here I don't have to write the psi anymore, because the psi of 0 matrix here is the same as the psi of A by definition of scalar multiplication. Yeah? Right? So 0 multiply A, this means that 0 multiply with all the entries of A here. Right? So the result, of course, has the same sign as A, because this is contain all the 0 with the same sign as A by definition. This is an example. You see this, you know. Good. This is scalar multiplication, and I want to give you some property of addition, matrix addition, and then scalar multiplication, so that you are more convenient when working with them, with matrix addition and scalar multiplication. You know? So let's go ahead with matrix addition. So the property of this matrix addition. Of course, we are considering this A, B, C, which are matrices of the same size, so that we can add. Because you remember, matrix of different sizes cannot be added now. So if you want to add two matrices, the first thing you have to think about is this matrix should be of the same size. Otherwise, we cannot add. Yeah. So tell me, what is the name of the first property that you see in the slide? Tell me. Do you remember the name of that property?
Associative.
Oh, very good. The second?
Commutative.
Exactly. Commutative, yeah. And the third?
Neutral element.
Yeah, zero matrix simply is the neutral, but for the case of addition, this is called non-matrix. Yeah, zero matrix is exactly the non-element. Yeah, this is our convention at the beginning when the binary operation is written as addition, then the neutral element is called non-element, right? And the last thing is called every A will have opposite, will have negative A, such that A plus negative A equals 0. Okay, let me prove two of them. So the first one and the last one. Okay, so let me prove. So because institutively, you see that we are defining the addition using the addition of the field K. Therefore, the matrix addition should inherit on the property of the addition in the field K, because we define very naturally, that at corresponding entries. So let me prove at least the first property and the last property, so that you can be familiar with the matrix addition. Good. Let me prove. Okay. Let me share. Good. Let me share this whiteboard. Okay. So for the first property, let's suppose A is of the form AJK, B is of the form BJK, and C is of the form CJK. And both of them are n by n matrices, And now let me add A plus B and then plus C. This means we have so let me compute A plus B. By definition, this is AJK plus BJK. This is by definition. Yeah. So I write here AJK once again, BJK, and add with CJK. And by definition, you have this plus this, AJK plus BJK, but we have to make a bracket here because this should be done first, and then we add with CJK. But this is the addition in this. We have this addition in K, so a field. That think about K as a set of real numbers so that easy for you. So don't be worried about K. Every element in K can be computed addition or multiplication exactly the same as in R. So let's think about K as R because it's actually the field. And in K, in this field, The addition has property of associative already, no? Therefore, I can put brackets anywhere I like, right? But then you have here actually a JK, the matrix. Yeah? Now I write this matrix as a sum of two matrices, is JK plus CJK. But now this is actually A, and this is actually B plus C. The matrix with this entry here actually B plus C. And we are done, yeah, QED. So this is a proof of the first entries, the first property. And the last property, 4. So I take again A as here. I don't want to rewrite it as a put it here again. And then minus A is simply minus 1 multiply A as what I wrote at the beginning. And this is simply minus 1 multiply the matrix of the form AJK. And by definition, I multiply minus 1 to every AJK here. So we will obtain minus AJK. So this means when you add A plus minus A, you have our matrix A sub JK plus this minus A sub JK. And by definition, this is AJK minus AJK. But this is 0. AJK with plus negative of AJK is clearly 0. So we obtain 0. In this case, I don't have to write the sign of 0 here anymore because it should have the same sign m by n as a and as minus a here, clearly. But you have to write a little bit bigger. Yeah, a little bit bigger. You can write 0, but a little bit bigger than the small 0 number to indicate this is a 0 matrix. Okay, so now this is our property 1, 2, 3, 4. So I proved only 1, 2 property. And now I ask you if I put, okay, if I put m by nk, the set of all matrix of the size m by n, so m rows and n column, so that we can do the addition in this set. Now, then what is this structure? What is the name of this structure? So this m by nk, the set of all, okay, I write here, set of all m by n matrices with the entry in K. Can you tell me what is the name of this structure? Using the property from 1 and 4, immediately what you obtain? Tell me. Yeah, it is a commutative group, no? Or a Boolean group. A Boolean group. If you like this name of mathematician, Norwegian mathematician. Okay, this is what I want to tell you in the slide. Now, so I return to the slide. I return to the slide and tell you the story. Okay, as above, I denote by this m n by n k the set of all m by n matrices with the entries belonging to k. Yeah, the sentence a little bit longer than in the whiteboard now. Think about k and r, and it's simply, of course, k can be any field now, but let's think think about k as a set of real numbers so that you can have a good feeling, you know. Then actually this is a commutative group, as somebody already said to you. He recognized very fast now. And whatever, you have some more property of scalar multiplication that I listed here. And if you like, we will prove one of them. Yeah. So it's proof. So here you have alpha and beta numbers, real numbers, a complex number, whatever. So it's belonging to k means that's number. Then you have the scalar multiplication. So you can multiply a number with the matrix in a way that you multiply this number to every entry of the matrix. It's very simple. This is simple for children now. So it satisfies 5, 6, 7, 8. So I listed here. So it is distributive, yeah, with the sum of matrix, and the multiplication here is also distributive with the sum in the QK, right? You see this, and it has property of associative, right? So we can, in the series of multiplication of numbers and matrix, you can put brackets anywhere you like. Therefore, you don't have to put brackets anymore, because wherever or when or wherever you put brackets, still nothing changed. You know? Therefore, we don't have to put brackets. And the last thing, this is very formally, but I write here so for later, you know. 1 multiply A, of course, A, because 1 multiply every entry of A does nothing, you know. So you obtain 1 multiply A from A. So let's prove the first thing, you know, this property of distributive property between the scalar multiplication with matrix addition. Yeah. So let me return to the blackboard, to the whiteboard. It's not like this board is totally white. So I return to the whiteboard and show you the proof of the first property. The second property or the other property is just easy as the first, you know. Good. So this property 5. So we have alpha in K and AB in this M by NK. No? I write this way to guarantee that AB has the same sign, M rows and N columns. So now I multiply A alpha with, you don't have to put point here. So it's redundant. Use the try A multiply alpha multiply A plus B. So suppose A is of this form AJK and B is of the form BJK. And this is alpha multiply something like AJK plus BJK. And then you have, by definition of the scalar multiplication, this is alpha multiply on the entry. But this is, so this is a multiplication in the field K. What we are doing here is in K, but K is a field already. And in the field we have this property of distributive already. So you have, this is alpha AJK plus alpha B sub JK, right? And at the end, therefore you obtain this is alpha AJK plus alpha BJK because of the definition of the sum of two matrices. But now you can draw it out because this definition okay, now you can write immediately this is alpha A, because the definition of scalar multiplication, alpha A means that I multiply alpha with every entry here. So immediately I can draw alpha out and the remain is A, no? Alpha B. So we are done. Okay, this is property 5, and the proof is the similarly as what I did before. No? It's easy. Now it's no problem. Okay, now we are returning to the slide, and I show you some more property. Yeah, the other property can be proved easily in the same way. Good, and now here I have 2 more property related to the transposition I listed here, so that you can use when you are working with exercises, so that it's convenient for you when you're working with exercises. Now, this is transposition of a sum is a sum of transposition. It's clear, it's easy, you know. And transposition of a scalar multiplication is simply you can draw alpha out. So you obtain alpha multiplies A transposition. You know? Okay, actually we are on time. This time is actually up, so we finish this year. And I finish this year and see you next time, right? Wish you all the safe, stay safe.
Goodbye.
Bye bye. I
Goodbye,
am
teacher.